Purdue. We're going to present Nick Miller from University of Oklahoma, giving us a gentle introduction to superrigidity.
Hi. Well, thanks for the order. Thank you to the organizers for the invitation to speak and for putting me first. So the goal of today is to give you sort of a broad strokes introduction to something called superrigidity. My goal is not to give you a bunch of proofs and techniques, just to give you a little motivation for some theorems that come from the 70s and maybe, if I have time, sort of what's not known in some cases that I'm particularly interested in. So along those lines, I just want to say that if you're taking notes, I'm going to give a quasi-correct talk, but there's only going to be about 90 to 95% correctness. So any statement I write down, there might be an adjective missing that I don't want to talk about. I'll try to say when that happens, but you can press me for details at any point this weekend. Just fact check everything. Okay. So let me start with the broad stroke question. So basic question. Is this big enough, by the way? In fact, yeah? Okay. So basic question. So given your favorite group, given a group, gamma, describe its linear representation. So what do I mean by that? I mean, e.g., its homomorphisms from gamma into, let's say, SLN of K. And here, today, I mean, in general, when you ask this question, you can think of K as being anything you want. But today, I want K to be, well, I saw there's a number here, so a local field of characteristic 0, if that's your kind of thing. But by that, I mean it's either R, C to complex numbers, or if you like p-adic numbers, then you can allow it to be p-adic. Okay, so these are the three things I want to talk about. You can ask this for finite fields. Let me just start here. Okay, so I'm looking at determinant 1 matrices with coefficients inside these fields, and I want to describe every time I have a map into some. Okay, so before we start to talk about groups in general, let's start to work through some super simple groups. And every group I write down today is going to be infinite. Apologies to people who like finite groups, but let's just start with something like the integers. And then if I want to describe for you a homomorphism from the integers into SLNK, well, this is completely determined by where I send 1. Right? So then any map like this is determined by the matrix where I send 1, because Z is generated by this. By the way, I'm not requiring anything about injectivity, surjectivity of this whatsoever. So in this way, what we see is that if I look at the representations, these linear representations of my group gamma, so I'll use this to denote the set of representations, then this is in one-to-one correspondence with matrices in SLNK, just by choosing one and defining my homomorphism to be powers of that thing. And so in particular, you get that the set of representations is just all of SLNK. Just choose your favorite matrix and you just define them out to the integers by taking powers. Okay, so this is a simple example where we can describe all possible linear homomorphisms. So let's start to get a little bit more complicated. So now what might you do? You might ask for something like the free group on, let's say, K generators. So let's call the generators maybe gamma 1 through gamma K. And again, what should a representation be described by? Well, the free group has no relation. So any homomorphism, I can again just choose K different matrices. And I can define a map from the free group into SLNK. So again, anytime I have a representation, it's determined by where I send each of these generators, which are my AI. And so in this way, you see a very similar phenomenon as this case. You see that all of the representations just look like SLNK, and I take this K times. Okay. So far, so good? And again, the image here could be trivial. You could just choose the trivial matrix, K times, but it could be interesting. No requirement on anything about the kernel or the image. Okay, and again, let me just choose maybe one more example. So here, I can choose maybe the free abelian group instead of the free group on k generator. So I can just take d to the k. And again, our representation is determined by where the generators go, except now you have to worry about a relation. So in particular, rho determined by where I send each of these. Except now I can't just choose any matrices. I have to choose ones that commute. Okay, so such that, so where AI and AJ commute. Okay, so in particular, the representations of this one, they look like couples of matrices where the commutator of AI and AJ is the identity, and this gives you all of the representations. Okay. So by the way, I want to say, now we're starting to see some structure. So when my group has some relations, you have to see the relations reflected in the representation that you choose. So let me just make one quick observation before we go on. So observation, which I'm not going to use necessarily now, but I might use it later, okay, which is that if I have a surjective homomorphism between groups, then that tells me something about how these representations sit inside of each other. So if, let's say, gamma surjects some lambda, then representations of lambda embed just as a set into the representation. And how does this map go? Well, if I have a representation here, a linear representation, let's call this one maybe pi, what can I do? I can compose it with the surjection to get a representation of the big group. Okay, so what you do, you take a representation here and you map it to the composition of my circle here. And then you get the map between these two. And so just to give you some concrete example, if you look at the free group and z to the k, you can see this explicitly. So e.g., if I take the free group and I abelianize it, so that is, I make every generator commute in the free group, then what do I get? I get z to the k. And here you can kind of explicitly see that here the representations is just k tuples of matrices, a1 through ak, and here I'm requiring some.
Do you want the commutator to be 0?
Here's the identity matrix. Yeah. So the trivial element in SLN is the identity matrix.
Isn't the trace of the commutator 1 is 0? Take the trace of both sides. You did different things.
No. Maybe we just write down that expression of the commutator. Sorry. Okay.
Oh, okay.
This one. Yeah.
Oh, okay.
So all of these have determinant 1, so when you take determinant. Okay. Yeah, this is not like a lead bracket. All right. Good. Other questions? Yeah.
Is there a reason we're looking specifically at SL instead of GL?
No, take your favorite linear group. Yeah, so thanks for that question. So here, when I'm looking at linear representations, I'm happy with your favorite linear group. Okay, so if you want GL, if you want SP, whatever. And in fact, I'm being a little disingenuous calling this rep gamma because secretly I should report what the target is too. Okay, but I told you it's a 90% correct talk, so it's going to be built into the routine. Good. Other questions? All right. So these groups, you can actually describe completely, at least in SL, like all the representations possible. Okay, but now, what I'm personally interested in is more complicated groups. So the question is, what about more complicated? Of course, this doesn't necessarily mean much, but let me give you some examples. So what do the representations of more complicated groups look like? So here are some explicit examples that I'm interested in. So first of all, let's let gamma 1 just be pi 1 of a surface. Closed genus G surface. So here, if G is at least 2, then this is A1, B1, up to AG, BG, such that the product of all of the commutators is the identity. Oops, almost hit that. Okay, so this is a surface group of genus at least 2. Here's another group that I'm particularly interested in and will be a big focus of the talk today. What about SL3C? So here, take 3 by 3 matrices with integer entries, determinant 1. What do all the representations of those things look like? Okay, and maybe gamma 3 is pi 1 of your favorite manifold. Hopefully it's not the sphere, but this is a very interesting group in general. Okay, so I want to describe what all the linear representations of these complicated groups look like. By the way, if you just take SL2, answering the question for even these first 2 groups is very complicated. Okay, so for those of you who know something about hyperbolic structures, you might know what all the discrete faithful ones look like, but it's actually more complicated if you ask for all of the representations into SL2. For this one, if you don't already know what I'm going to talk about today, it's a very hard question to study what is SL3C, what are all the maps into SL2. Okay, good. So this is the basic motivation. So any questions before I go on? Okay, so I'm going to go on to a little digression and tell you about pi 1 of my favorite manifolds. So here this is part of something that I'm going to call lattices. And I'm not going to assume that anyone here knows what a lattice is, so let me just start with the following motivational example. Okay, so lattices in some sense are going to be a generalization of the following. So here I'm going to let X be just Rn, and here I'm not just thinking of this as a topological space, I mean with the Euclidean metric on it as well. Then the isometry group of Rn looks like what? Well, all of the isometries of this thing are either given by translation, by adding some number, or rotating. Okay, so this looks like Ln cross semi-direct Rn. So here, this one here is acting by translation on Rn, and this one here is the linear action by rotation. And well, these 2 things, they don't quite commute, but there's a semi-direct product relation. Okay, so every isometry, meaning everything that preserves distances in Rn, can be written as a product of rotations and translations. Okay, now this group here, G, it acts on Rn transitively. So i.e. every point in Rn can be moved to another point, in fact via translation. Okay, so I can always move one point to another. Okay, and moreover, the stabilizer of this 0 is the origin. The stabilizer of the origin in Rn, well, translations don't stabilize the origin, but rotations do stabilize the origin. So the stabilizer of a single point is given by this orthogonal group acting by rotations. So let me call this one K. And so what does orbit stabilizer say? It says that I can write X now as the quotient of the orbit of a point, but the orbit of a point is everything because this group acts transitively, mod the stabilizer of a point, right? So orbit stabilizer tells me that Rn, which is just my X, is the same thing as G1. And in fact, okay, in this case, this is a normal subgroup, so actually this is a group now. But we know Rn is a group just by adding things. So in fact, you get a group structure here. That won't happen later on, but I just want to point it out here. Okay. So, this is just R2. And here, On is acting by rotating this, and R2 is acting by translating it. Okay, but now, what I claim is that I can use this sort of a picture to build myself an interesting manifold. So how am I going to build an interesting manifold? Well, I can let Z to the n act on X via integer translations. Okay, and then what happens is I can quotient Rn then by this copy of Zn. So then I can take want to call this, I want to call this, well, maybe I don't want to do this in it. Yeah, okay. So then, you take Rn, you quotient by this Cn, and what do you get? You get the torus. Okay, so in particular, in my picture of R2, I'm quotienting by integer translations, so I get this integer grid. And when you quotient, what do you get? You get a fundamental domain like that where you identify the two walls, and so you build the two torus in this way. Right? So I build this manifold, and moreover, pi 1 of this Tn is exactly the thing that I quotiented by. Okay. And I get a quotient that way. Yeah?
The reason you want to write your quotient this way?
Because I quotiented by k on this side, so I better quotient on the other side by the time. But it's, okay, depending on who you are, some people quotient on the right, some people quotient on the left, and they're equivalent. So if you prefer to quotient on the right, that's totally fine. But here, usually, so here, if I'm thinking of this as being g mod k mod this z to the n, then I need this quotient to be on different sides. Yeah. Yeah. Okay, other questions? But it's just cosmetic, like it doesn't, you know, you can flip the sides on everything. Other questions? Okay. What's even better about this picture is not only do I topologically get a torus when I do this, I get a metric induced on this torus. Okay, so why is that? Well, this Zn, the key point is that when I act by integer translations, it's acting by isometries in the universal cover. It preserves distances. And when I preserve distances on this universal cover, as long as the action is sufficiently nice, I get a metric induced here. And how do you measure distances between 2 points? You take your favorite 2 points, you look at all possible lifts into the universal cover, and then you minimize the distance between all possible lifts, and that precisely gives you the metric downstairs. So there's something special about acting by isometries. It tells me that I also get a Euclidean structure on this torus. So this torus is not round, it has a Euclidean structure on it. It's actually flat. So locally, it looks like you're sitting in a copy of Rn. Okay? Okay, but I told you I want to study more complicated groups. I don't want to study abelian groups. Okay, so I need a non-abelian generalization of this. Okay, so here's the non-abelian setting. Oh, we started at 5 after. Oh, good. This is scary. Okay. My nose. Okay, so here, I'm going to say a word that some of you will like and some of you might not, but I'll give you examples, I promise. So here what I'm going to do is I'm going to let G be a simple real V group, okay? Whatever this thing is. And when you have such a thing associated to this, what you can do is you can produce exactly the same picture. Okay, so the point is that associated to such a thing, you get X, which is called a symmetric space, which you can write as G mod K, where K looks exactly like this thing. So what's one property of this K here is the maximal compact subgroup of this group. So On cross Rn, both of these things are real, they have a topology on it, and the maximal compact subgroup is given by this orthogonal group. And there's a similar story here. You have some K, which is a maximal compact subgroup. And you can write this thing as G mod K. And moreover, you know that G is equal to the isometry group of this symmetric space. Okay, so this is like differential geometry class in 20 seconds. So let me give you some examples. So if you've never seen this before, this is going to mean absolutely nothing to you. So let me give you the 2 key examples that I want to focus on today. So here's key example 1. So I'm going to let G be SLNR instead of Rn. Semi-direct. So here, I want this to be SLNR. So here this is determinant 1 n by n matrices. Okay, and then what's a maximal compact subgroup of this thing? It turns out that K, which is the maximal compact subgroup, is given by SON. So I guess I can define O up there. So this is A, such that A transpose A is the identity, and the determinant of A. Okay, so this is the biggest possible compact subgroup you can find in SONR. Okay? And, well then, the corresponding symmetric space, I'll call Xn is equal to G mod K. So you take the quotient of these two things. Let me point out, this SON is not normal inside of here anymore. So this quotient, it does not have the structure of a group. Okay, it's just some random coset space, but it turns out to be a nice Riemannian manifold, which is simply connected. Okay, and well, if you like interpretations of things, it turns out that this is actually, this G mod K, whatever it is a space of matrices. Okay, so this is actually, what do I want to say? It's positive, definite, symmetric, determinant 1, n by n matrices. So actually, if you want to look at the space of all symmetric matrices, which are positive definite, this actually has a nice Riemannian structure. You can write it as SON. I'm not going to write down the correspondence, but if you want to bug me later, I'll tell you about it. How does, okay, maybe I'll just say. Okay, so if you look at this set, how does G act on this set? It acts by G transpose times the matrix times G. And you can check that the stabilizer of the identity is a copy of SON, and you can check that it's a transitive action. Yeah?
Is your maximal compact subgroup always going to be the stabilizer point?
In this case, yes. Yeah. So,
In the general case, or?
so when G acts transitively on the space, so this G, where is it? This symmetric space that G is acting transitively on, the K will always be the stabilizer. Okay, other questions? Okay. So that's example 1. Oh, there's another board as well. Oh no. Okay, so what's example 2? This one might be slightly more familiar to some people in this room. So here's the example 2. Except I might write it in a way that's less familiar. Okay, I'm going to look at hyperbolic space. Okay, so here I want G to be SON1. So what is SON1? It's all of the n by n matrices which preserve a certain quadratic form. Okay, so this is such that QAX is equal to QX, and what is Q? Q of X is equal to x1 squared plus up to xn squared minus xn plus 1 squared. Okay, so it preserves this quadratic form. Okay, this turns out to be a very large group. It's not. Okay, and then what is K in this instance? It's a copy of the orthogonal group. And what is the corresponding X? Well, let me draw you a picture. And let me call it Yn in this particular instance. So Yn. So this is all of the X in Rn plus 1, such that when I look at this quadratic form and I evaluate it on X, I get -1. Okay, so in particular, this thing looks like one of these things that we call in calculus like a hyperbolic paraboloid or whatever. Okay, so this thing is Q of X equals -1. Now again, some experts might be cringing in the room. I told you that this was a 90% correct talk. There's some small lies inside of each of these things. Secretly, if you plot this equation, it's 2 sheets, so you should restrict to 1, etc., etc. But again, this is more or less correct. Okay, so this is the corresponding symmetric space, and you can write this symmetric space as G mod K. And again, just to follow up on the question that was asked, this K is the stabilizer of a single point in this hyperbolic space, and G acts transitively. So all the stabilizers are conjugate when G acts transitively. Good. Okay, so let me just make a quick remark. Oh yeah, and also I should say, this Yn is very frequently written as Hn, which is hyperbolic space. Okay, so this is hyperbolic n space. So let me just make one quick remark here. So very frequently, I think when we teach hyperbolic space, we teach the upper half plane. So this thing, when n is equal to 2, is exactly the same as the upper half plane model, if you've seen it before. Okay, so y2 is the same. It's isometric to this one, this copy of h2, if you've seen it before. So here, SL2R acts on this thing by Mobius transformations. Okay, but also, turns out that this space of positive definite symmetric matrices, n by n, is also the same thing when n is equal to 2. Okay, so this is also x2. However, x to the n is not the same as y to the n. Y to the n is so here, this isomorphism means isometric. Good. So these are the two symmetric spaces that I'm interested in. And again, I want to think about lattices in these things. So what am I going to do? I'm going to look at my friend the torus, and I'm going to try to do something exactly analogous to that. Okay, so here, here's a fact, which is that if I take some subgroup of G, which I want to remind you is the isometry group of this symmetric space, which is discrete, then the corresponding quotient space, E1 gamma, which I want you to juxtapose with that quotient space over there, is a manifold. Locally modeled on X. Okay, so again, one thing. This is again a small lie, okay, but it's a sort of innocuous lie. And you should really ask for this thing to be torsion-free if you want this to be. Again, that's just a very small lie that's not a big deal. So again, what do I mean by locally modeled on X? Well, if you look at the torus again, if I stand on this torus everywhere around myself, I locally look like I'm living in Euclidean space, right? I look like I'm living on a flat torus because I stole the metric from upstairs. Well, if I have a discrete subgroup and I take this quotient, the same thing happens. Okay, so there's a covering map, but not only is it a covering map, it's like, it's a local isometry. So in particular, every neighborhood of me on this downstairs manifold looks like I'm living upstairs in the universal cover. Okay? So what is a lattice after all of this, and what are my favorite types of groups? There are ones which look like the torus in the sense that upstairs in the universal cover, we don't like it, well, for two reasons from the perspective of groups. So one, it's simply connected, so that's not that exciting from the perspective of groups. But also, if you're doing some kind of geometry, sometimes the fact that it has infinite volume becomes a problem. But when you notice if I quotient it by Zn, I get a torus which now has finite volume. In fact, in that case, it has volume 1, right? It's the same as the area of a fundamental domain. So you get volume 1 when you blew up this square. Okay, so a lattice is going to be this picture, but where I ask that this thing has infinite volume, where I ask when I take the quotient, I get something with finite volume. Okay, so here, gamma is a lattice. So maybe I should write definition. Gamma is a lattice if the volume of this x gamma is finite. Okay? Yeah.
You want E there or you want S there?
Oh, thank you. Yeah, appreciate it. Thank you. Very good. Other questions? Yeah, I'm very prone to typos on the board, so thank you. Okay, so lattices are the ones for which, when I take this quotient, I get something of finite volume. Okay. So let's just do some examples. Oh, I shouldn't have erased the surface group. Oh well. Okay, so just as an example, if you take phi1 of a closed surface group, which lives inside of the isometry group of hyperbolic 2 space, and again, I want G to be at least 2 here, then this tends to be a lattice as long as you took the embedding rate. So then, let's call this gamma. So then H2 mod gamma is something that looks like a genus G surface. And genus G surfaces have finite volume, they have finite area. Okay, so this is an example of the kind of thing that I'm talking about. And this is one of our complicated groups, so it actually fits into this whole geometric setup. Okay, you could also take, similarly, you know, if you take pi1 of your favorite finite volume hyperbolic manifold, and this will give you an example. Your favorite hyperbolic manifold. Okay, but another example, which maybe I'll write on this board. Oops, nobody saw that. Is what are called arithmetic subgroups. Arithmetic subgroup. So arithmetic subgroups are famously not defined ever in talks, and for good reason. But frequently we just say these look like integer structures on G. Okay, so these are quote unquote integer structures. It's the kind of definition where if you know it already, then you don't need to see it, and if you don't, it's not useful to see it in the talk. Okay, so, but let me give you examples. So here, for instance, if I take SLNZ, this is an arithmetic lattice inside of SLNR. So here you literally think of this as being like I take the real numbers and I just swap them out for the integers. And why do you do this? Well, the integers are discrete in the real numbers, and so for free you get a discrete subgroup. The challenging thing is to prove that actually it's a lattice, so actually that you get finite volume when you take the quotient. That's actually a big theorem, but in general this is true. Okay, and similarly, if you like hyperbolic space, you can slip the real numbers for the integers and you get another discrete subgroup. So here, you can take, for instance, SON1Z inside of SON1, and you get another integer structure. But let me not make it seem like there's only one integer structure. In fact, on SLNR alone, there's lots of different integer structures, and number theory can actually classify them all. Okay, so these really are born out of number theory. They're born out of some integer structures. It's like the real vector space. There's lots of different integer bases. Right? Any questions? Okay, so let's get on to, so this is sort of my digression on, for me, what are interesting groups. So I like these groups lattices that give me sort of very complicated groups, which give me fundamental groups of manifolds that are built out of symmetric spaces. And now I want to go back to the question of rigidity of representations that we had in the first part. So here, this is sort of part 3, which is going to be superrigidity. But before I give you the full sort of fledged statement of superrigidity, I want to give you a warm-up thing that's going to not look like a linear representation at all. So here's a warm-up observation. Okay, and what's the observation? Is that if I ever have a map, so maybe I should say given any homomorphism, so here, this is from Z into R to the n. So this is a homomorphism. Let me call it rho. By the way, notice I changed the story on you. This is not a linear group anymore. This is R to the n. It's not GL or whatever, okay, or SL whatever. But here it's just a copy of R to the n. Then let me write the conclusion, and then let me tell you what it means. So there exists rho hat from R into R to the n, which is a continuous extension. What does it mean to be a continuous extension? Well, Z, it also lives inside of the integers. Okay, so Z injects inside of R. And what does it mean to be a continuous extension? It means that I can complete the diagonal. Okay, so it means that there exists some rho hat like this. But not only is there a homomorphism rho hat, it's also continuous as well. Okay, so there's two things that you need for this. The first is that rho hat is continuous. And the second is that when I restrict rho hat back to the integers, I get the original representation that I started with. Okay? So anytime you have a map from Z into Rn, you can always build such a thing. Okay? Whoops, no. Oh, did I use that? Well, I don't know where I am anymore. Okay, so let's just go back here. Does anyone see the proof? It's a one-line proof. Okay, I hate when people ask about some proof. Oh, yeah.
Just a real number is a in it, homomorphism at a z, you just pick which vector 1 goes to.
That's right. So you define. So you just sit there and you think about what this thing has to look like for a second, and you realize that it has to be r times row of 1. So wherever 1 goes, you just take a scalar multiple of that thing. And what you check is that this satisfies criteria 1 or 2. In fact, you can check that this is actually a linear map. It's just scalar multiplying, so it's a linear map. Okay? And you can check that it restricts onto the integers using the original representation. So just homomorphism properties will give you a one-line calculation for this example. Right? Okay, so here's your exercise. And again, here's exercise 1. That this is not just a fact about the cyclic integers, it's a fact about z to the k. So this works for you. So if you're already bored, you can try to prove this. It's not too complicated. That'll give you a harder exercise. Okay, so then the next question is, well, I sort of changed the story on you. Here, this is like a very linear situation. I asked if the map goes into Rn. Okay, what if I ask for a linear one instead? So what about if I look at z to the k, let's just do z for now, okay, into, let's say glnr. Okay. By the way, this g is not so important. The same thing will work for sln, but it's easier to show you an instruction. Okay, so. Well, the answer is, even though it doesn't look like that big of a deal, there's actually obstructions now. So you can't ask for this kind of continuous extension. Okay, so there exists obstructions to continuous extension. So let me just show you. I changed this to GL because it's sort of the easiest thing I can show you. You can always put GLN into SLN plus 1, by the way, so it's not that big of a deal. Okay. So what does the obstruction look like? Well, let's assume that there exists a continuous extension. So if there exists a continuous extension, this is rho hat from R into glnr. Well, what does that tell you? This is a continuous map. And then what can I do with this map? I can compose it with the determinant. Okay, so then you have a map here, which is called determinant, which goes into r star, so this is r minus 0. And this is also continuous. Determinant is actually a polynomial map. Okay, you can write it as a polynomial with variables. So it's definitely a continuous map. Composition is continuous. But then what do we know? R is connected, and so this tells you that the determinant has to land in the positive real numbers. Okay, so the determinant of rho hat of r, it has to be contained in 0 and infinity. Well, it has to be contained in one side, and then you know the identity has to go to the identity, which has determinant 1. So that tells you it has to be positive. Okay? But now, why is that a contradiction? Well, I can give you lots of representations where I send the identity to something with negative determinant. Right? So, you know, you can put all 1s on the diagonal and then a -1 on one coordinate, and that's something with determinant -1. So, but you can't possibly extend them to something continuous. So this is a contradiction because we can find some rho such that determinant of rho of 1 is negative. So it can never possibly extend to something continuous because these ones always have positive determinant and these ones might not. So again, just map it to something order 2. All 1s on the diagonal with 1 minus 1. That thing has determinant -1. And then you're out of luck. Okay, so here's your harder exercise. And okay, this might, I mean, the proof I know requires a little bit of lead theory, but not a ton. Okay, which is that, you know, this is unfortunate that you can't extend these things, but you can virtually extend them. Okay, so for every, so maybe I'll write it this way. So every representation from z to the k into GL and R virtually extends. So virtually. So what does it mean to virtually extend? So this here is my gamma. It means that you can find a finite index subgroup of this one where you actually get what you want. Okay, so i.e. there exists a finite index subgroup such that gamma prime fits into the diagram where this goes to GLN R, this goes into R to K, and again, you have this continuous map, rel hat, which extends this. So here, this is the original representation restricted to gamma.
Is connect is the only obstruction?
What?
Is connect is the only obstruction? Because it's lands in the identity component instead.
Yeah, that's right. Okay, so Dave solved the exercise already, but I'm not expecting to solve it that fast. Yeah.
Can you repeat again why the composition determinant of row has to be in the box?
Yeah, that's right. So here, just to reiterate, so here, this R star, right? It's R minus 0. The determinant can't be 0 for this GLDR. And each of these maps is continuous. So when I take the image of something which is connected, then it has to land inside of a connected component of the thing in the image.
And then why can't it be negative?
Right, sorry. So the point is that this is a homomorphism. So the identity here has to go to the identity here. But then the identity matrix has determinant 1. So it has to land in the positive ones. Yeah. Sorry, I didn't write. Yeah, I skipped a step when I wrote it. Yeah.
The Z is not connected, so.
That's right. So this is why this doesn't work for the. I mean, this is exactly why this being continuous is a huge problem for you. But that's right. Z is not connected, and it has the discrete topology usually. So you know, if you take the continuous image, you can't say anything about where things land. But here, you can. That's right. Good. Okay. Other questions? By the way, like determinant's not the only obstruction. So the point is that you can map onto a finite order element, and then that thing won't extend. So you have to just pass to some subgroup. Questions? Okay, so all of this is supposed to be sort of a warm-up to the statement of superrigidity. So in this sort of instance, I just want to sort of emphasize what's happening here. You start with something discrete, and I'm taking some random homomorphism of it, and all of a sudden out of that, it lives inside of something continuous, a real thing, and I can say that this representation from this discrete thing, which is completely disconnected, actually came from some continuous object. Okay, and similarly, z to the k is a completely discrete thing. It's just an integer grid living inside of rk. Why should I think that I can, build? I mean, if you're just looking at functions, not homomorphisms, you'll never be able to build something. I mean, what am I trying to say? I mean, yeah, you can extend in lots of different ways, but here, I'm saying that every representation of this discrete object is completely characterized by the continuous object that it lives inside of. Okay, and this is a phenomenon which is called superrigidity. Okay, so here's the theorem. So let me just say this is Margulis' superrigidity. Part of the reason that we want the Fields medal is the following theorem. And here I'm going to state it in a special case, and then I'll tell you what's the real thing. So here, if gamma lives inside of SLNR, it is a lattice. N is at least 3. So here I want to point out that SLNR when n is at least 3 is very much not hyperbolic. Okay, so it's whatever that means. Okay. Then and rho is a representation again, and here I'm going to do something sort of tricky. I'm going to just look at its target inside of some. Well, let's make this a k. Okay, so inside of some SLNR. SLNK. So here this K is this field from before. So again, remember this can be either real, complex, or yeah. Okay? And, Okay, there's going to be something slightly technical that I'm going to do. I'm going to take the Zariski closure of this image. If that means nothing to you, think of this as being the smallest possible linear subgroup that the image sits inside of. Okay, that's what the Zariski closure will be. No worries, this won't appear otherwise. Okay, then the statement is the following. So either one thing happens, so either rho of gamma is compact. So that is, the image is compact, so that's one possibility. And the second possibility is that exactly what we just saw before that happened for abelian groups happens for more complicated groups. Okay, so there exists, let me just say it this way, rho virtually extends to a continuous homomorphism rho hat, which goes from G into. Okay? Moreover, even in this case where it's compact, if you allow your field to be R or C, you can even classify those ones. Okay, so moreover, if K is R or C, actually, this compact case is a special case of the second one where I allow you to apply a Galois homomorphism. So actually, then rho of gamma is always equal to the composition of some rho hat, just like in this case too, and then I twist by some Galois automorphism. So there, sigma Galois group. Let's see. Okay, so what does this mean? This thing lives inside of matrices over R or C, and so when I apply a Galois automorphism, I just apply this to all of the entries of the matrix. Okay, so you just conjugate it by something. So it's a composition of a continuous map, but maybe then a field automorphism. So you can actually classify it. Also, again, if you want to apply this, you should be careful. There's a slight adjective I'm not saying, but yeah, maybe I want. Okay, it's a statement. I'll try to clarify through some examples. Second, I thought you might answer one of the questions. Yeah.
So there are no restrictions on little k.
What's this one?
Gamma, or above that, or are they both SL in one?
No, yeah. So K and N can be. Oh, yeah. Here, yeah. I want K at least. Yeah. That's right. Oh. Well, I wrote N at least 3, but then I changed it to a K, so maybe that makes it 3. Yeah. There we go. Yeah.
The G at the bottom here, for clarity, is SLKR.
Yes. Thank you. Okay, so let me make one technical remark before we move on. And again, this is just for people who know what these words mean, and don't worry if you don't. This has nothing to do with SLK. It's true for every higher rank real simple groups. Okay, so this is still true for all G of real rank. Okay, so what real rank at least 2 means is that this is true for every isometry group of symmetric space that's not hyperbolic. Okay, so all of the ones which are not hyperbolic, this is true for. So that's what this is called higher rank in the literature. Anyways, but SLKR has rank K minus 1, and so K at least 3 tells you that the rank is at least 3. Okay, so let me tell you some applications. Including one to the original question that we asked. So first of all, why is this theorem sort of interesting? Well, one, it tells you what all possible automorphisms of your lattice look like. Okay, so in general, if I hand you a finitely generated group, and I ask you, what do all of the automorphisms of this group look like? That's a super hard question to answer. Okay, there could be lots of them. Okay, if I ask, in finite group theory, we know how to sort of do these things, but in general, this is a super hard question. But this sort of a theorem will tell you exactly what all possible automorphisms look like. Okay, so it tells you that the automorphisms of gamma are precisely equal to the automorphisms of SL, the continuous ones. And now, that might not seem like a big deal, but this is a continuous group, and it's really easy to understand what all the automorphisms of SLK are. Okay? In fact, Lie theory tells you exactly what those things have to look like. Okay, so how does the proof go? It goes like this. So I start with gamma, and let's say you have an isomorphism of gamma to itself. Well, this first gamma, it lived inside of G, and this second gamma, which is the same one, lived inside of G. So here, this is your representation, rho, and well, superrigidity tells you that this thing extends. Okay, so then you get a continuous extension, rho hat. So in particular, rho hat gives you an automorphism. Okay, so you just sort of apply this theorem and you get some statement like this. And in particular, this also tells you, for instance, that the outer automorphism group, so that is all of the automorphisms which are not just conjugation. I mean, this is the quotient of the automorphism group by conjugation. Okay, then this is actually finite. Because that's true for the automorphisms of G. So actually, there's a direct application to the automorphism. Okay, so what are some other applications? Okay, there's something which is called Margulis' arithmeticity. Okay, and again, I don't want to be so precise about what this means, but this tells you that all, I'm just going to sort of vaguely say that all lattices in such G come from integer structures. So they all look like these kinds of lattices that I gave you at the beginning of the talk. They all look like, for instance, you know, SLKC or something, some version of SLKC. So every time you have one. And the way that Margulis proved this is, it turns out that being an integer structure, you can, what's the word? You can, there's a criteria to being an integer structure which can be written in terms of representation. The point is then you apply it superrigidity. Again, if you want to know more about that, just pass me for details. Okay, okay, I had more applications, but let me move on. Well, okay, maybe let me just say one or two things out loud. So one, you also get triviality of flat bundles over certain manifolds. Okay, so there's a way from a representation to build a bundle over your manifold, and this tells you that all bundles built that way are trivial. Okay. But then I also want to say that you can classify all linear representations of gamma. Okay, so let me just give you an example of that. Okay, so let's just go back to this example that we had at the beginning. I have gamma, which is, let's say, SLKZ. And I have a map into, let's say, SLNR, where n and k might be different. Okay? Then what does superrigidity tell you? It tells you there's two options. Either rho of gamma is compact, or it tells you that this extends. So there exists an extension from SLKR into SLNR, which is a continuous map. And now, okay, there's some sort of, I mean, this is kind of a classical subject. What do all the representations that are continuous of SLKR into SLNR look like? I mean, there are books written on this kind of thing. You do some highest weight vector thing, and you can start to understand exactly what these representations look like. In particular, for instance, you should see that k has to be no bigger than n. So for instance, this would imply that k is less than or equal to n. Something that you don't actually a priori know at the beginning of my talk. Right? So it's not actually clear that I can't take SL3Z and map it into SL2R. I mean, why not? Right? So in particular, this tells you things like this. And if k is equal to n, you know exactly what this representation is. It's just the standard inclusion. Okay, for instance, maybe up to a translation. Okay, and it turns out that actually, in this case, I guess I don't have time to sketch the argument for you, but actually what you can prove is that the image of rho actually is finite. Okay, so maybe that's not 100% obvious, but the point is that when you're looking at case 1 here, and then you combine it with this moreover statement, what you would have to see is that this looks like a continuous extension up to a Galois automorphism. But then SLNZ has a bunch of unipotent elements, and then their image here has to be unipotent, and Galois automorphisms don't change the fact that things are unipotent. Okay, so, but then compact things don't have unipotence, so actually this case can be completely ruled out. Okay. Anyways, that's the argument, but I'll give you more details once. But the point is you get this dichotomy. Either there's a continuous extension, or the image is finite. Okay. So in particular, in this case, it's an almost injective map. You might have finite kernel, but you basically get an injective map. And here you see that the image is finite, and that's the complete list of all of them. There's nothing funky at all. These are all of the representations. Okay. Well, and maybe let me give one more example. Well, if you take, this is mostly maybe for number theorists, but if you take something gamma, and you take a representation into, let's say, SL and K, where now I'm going to ask that this K is p-adic, then Superrigidity tells you that that rho of gamma is always compact. And, well, the point is that, let me just say it, well, okay, I'll write it. So so why? Because if 2 happens, then there would be a continuous map from G into SL and K, where K is p-adic. This is continuous. Okay, but this is a real Lie group, and p-adic things are totally disconnected. Okay, so this is totally disconnected. But again, it's the same contradiction as before. You have something connected into something totally disconnected. That's a constant map. Okay, so in particular, you can never have a continuous extension. Well, okay, you get the trivial one, but the trivial group is a compact group. Okay, so that's the. Any questions? Yeah.
And just like a historical point or something, why is it called superrigidity? Is there some big rigidity?
Yeah. So there's various rigidities. There's a Mostow rigidity. There's a so various people have said that certain types of representations are rigidity. This kind of came after this, and this application 1 that I wrote earlier. This is basically what the statement of Mostow rigidity is. So this is some extra rigidity more than that. So it implies these other forms. I don't know. So it's called.
Okay.
But this is like the most rigidity you could basically hope for, so it's super, I don't know. There needed to be something else. Other questions? Okay, so let me just, well, I won't have time to say everything I wanted to, but let me just say, what about, so now this works for all higher rank lattices, and SLKR, this is everything which is not hyperbolic. So you might ask yourself, what about hyperbolic things? Okay, so what about hyperbolic spaces? Well, there's a cautionary tale. Which is that superrigidity cannot hold. So let me just tell you why. And the reason is that most hyperbolic manifolds surject free groups. For instance, surface groups do. And this totally screws you up for continuous extensions in a way that I want to explain to you. So you have gamma, and it surjects a free group. Okay, so here, again, the example, if you want, is if you look at a surface group of genus G, it always surjects a free group of G generators. And why is that? You just forget half of the generators. So you know, the surface group is A1, B1, all the way up to AG, BG. Forget all of the Bs. And that thing is a free group. And you just, I mean, you can map to this free group by you send each of the AIs to some generator here, and then everything else trivial. And that gives you a map to the free group, right? But then you can take the free group, and we saw you can do anything you want with the free group. So you can map it into, let's say, SOM1, and just choose your favorite matrices here as long as they don't lie in something compact. Okay? So choose something with infinite image here, which doesn't lie in something compact. But then this one, it also lives in some SOM1. And you can build a representation of rho such that rho, the kernel of rho, is equal to the image of rho, the cardinality, which is infinite. Okay, so you can build something with infinite image and infinite kernel. Yeah, just choose your favorite, generators here, which give you an infinite image, which is non-compact, and then make sure that you're destroying some things, like for instance the BIs, the AIs. Okay, then what would happen if this extended, right? So now, assume that there's a continuous extension like this. Well then, the same thing happens when you put hats here, right? But if you've ever played around with this group SON1, which, when n is equal to 2, this is just SL2R, there aren't that many normal subgroups of this thing. In fact, every normal subgroup is finite index or finite. Okay, so in particular, you can never have both of these things happening simultaneously. So you can never see that superrigidity holds. Okay? So one thing you can do at this point is you can sort of throw your hands up and say hyperbolic space is useless for superrigidity. Okay? Or I just want to leave you, okay, I have lots of questions, but I'm essentially out of time. So let me just leave you with a vague question, and then I'll say one word about what I mean by it. So here's something that's kind of open. Well, it's very open, and it's interesting. So here's a sort of open, vague question. Okay, so which is that what conditions on, let's say, gamma or rho or its image. So H here is supposed to be the image of this thing. Imply superrigidity. Okay, so here rho is. So these conditions could be anything you want. They can be geometric. They can be, I don't know, something simple. Now, what this sort of cautionary tale tells you is you shouldn't allow for every possible representation, because you can always factor through free groups, and free groups are the worst for superrigidity. Okay, but I might ask for something of my. So if I ask for something of gamma, I might want to ask for something of my manifold that I'm looking at. If I ask for something of rho, I might want to ask for some adjectives, like it doesn't factor through a free group, for instance, or I might want to ask for something here. So let me give you a theorem that you probably, if you know this theorem, you probably don't think of it in this way, but I want to advocate that it's in sort of a superrigidity. So this is what's called Mostow rigidity. And what Mostow rigidity says is if you have, in dimension at least 3, if you have two hyperbolic manifolds that have the same fundamental group that are finite volume, then actually they're isometric. But you can phrase this as a superrigidity theorem. So if you have rho from gamma into SON1, so this is also a lattice in SON1. So this is any representation such that rho of gamma is discrete and faithful. Then rho extends to some continuous map from SON1. So in particular, any such rho is induced by an isometry, but this is an instance of a superrigidity statement. So if it's discrete and faithful, then this thing won't lie in a compact subgroup, and then you'll see that this thing extends. So, here, what am I doing? I'm asking that this thing doesn't factor through a free group, for instance, I'm asking that I have something with a particular type of image, and when I do that, I can prove some type of superrigidity statement. Okay, so let me just finish now by saying here are some particularly, I think, useful adjectives that I'm not always sure how to use, but can sometimes be used. Maybe you should ask that rho is faithful. So in particular, this kind of stuff doesn't happen. Or maybe you should ask, if you know what this means, maybe you should ask that it's infinitesimally rigid. Okay, I will not define that, but this is another adjective that might lead you to some superrigidity statement. Okay, so if you put the right adjectives on your situation, maybe you can get some kind of statement, and this is sort of wide open in hyperbolic setting. Hyperbolic manifolds are extremely flexible, but we also don't know, but they also have sometimes superrigidity, and we don't know much. So just want to advocate that there's some interesting questions. I'll stop there.
Any questions? Yeah.
So I guess here we've seen evidence for the fact that you kind of need this higher rank stuff to happen, but I wonder if there's a nice layman's reason why, when you're trying to prove superrigidity, you want to do this, but then if you're rank 1, you can't do that. So that's where the assumption gets.
Yeah. Okay. So there is a nice layman's reason, but you have to dig into the proof to see it. I can tell you what it is, but and I'll tell you it right now. But it's not going to be clear why this is useful without digging into the proof of superrigidity. So the point is that in something like SLNR, there's a group of one parameter unipotent subgroups which all commute with each other and generate SLNR. So, and this is actually key in the proof. So the point is that you can look at subgroups that are of this form. So here, anywhere I don't put something is a 0. So this is an SL3R. Okay, so here, let me just put zeros. Well, okay, at least for the first one. So you have this one, and then you have the transposes of these ones, okay, in SL3. So here you have this one, okay, and then I need one more, but I ran out of board room, so it's going to have to be small. Okay, so this one, okay. It turns out that if you choose the order of these ones right, then you get a chain. If you call this U1 through U6, then they all each pair normalizes each other. So I can't do it in front of you and choose the right order, but you get a chain where UI is a normal subgroup. How do I illustrate? Actually, they centralize each other. That's what I should say. Okay, so you can choose these in some order to get a chain where each pair centralizes each other. And in Margulis' proof, this is key. And in fact, this is a key fact of all higher rank Lie groups, is that you always have a chain of one parameter unipotent subgroups like this, where each pair centralizes the next one and they generate the full group. So if you look at these subgroups, they'll give you all the matrices in SL3R. Now in rank 1, it's provable that you never have such a chain. Okay, so if you just think SL2R, right? So SL2R is a hyperbolic. It's the hyperbolic setting, and the subgroups that you get look like this and this one, and these two will never centralize each other. They don't commute, right? Whereas you can choose these in some order to get them to commute. So okay, that's the part that shows up in the proof. That's the key fact, and in fact, this commutation of unipotents is actually helpful for all kinds of things when you want to study the higher rank situation. And it's something that fails in rank 1. Now, that's not a particularly geometric reason, right? So you might complain that I didn't give you some take-home message. But on the level of group theory, that's what's happening. Yeah?
Are you going to tell us what's on the secret mystery?
Oh, yeah. Okay. Okay, so this whole part about the hyperbolic world, I was going to give you some more examples of this kind of thing. When you put various conditions, of this Mostow rigidity phenomenon. When you can put conditions of these things on here. So the secret word was actually that there's 4 types of hyperbolic spaces. There's a real hyperbolic space, a complex hyperbolic space, a quaternionic hyperbolic space, and a Cayley hyperbolic space. They come in families. Not only is there an SON1, there's an SUN1 and SPN1, and everyone's favorite Lie group, F4 minus 20. This is a real form of F4. I don't know. Don't ask me to define it, but this is a rank 1 Lie group, real Lie group. And the point is that there's a guiding philosophy in this world that real hyperbolic things are the most flexible. These are all hyperbolic, but these ones are the least flexible. So in particular, what I was going to show you, these things can't be super rigid. And also, Deline and Mostow proved that these things also can't be super rigid. But yeah, Corlett and Gromov-Shane proved that actually in the rank 1 setting you get rigidity of these ones. Okay, so these are all different types of hyperbolic manifolds. These ones are very, very rigid, they're super rigid, but these ones are not. But actually, as you move from here to here, it seems that the representations get more rigid. So I was going to give you a bunch of examples that actually come from the complex hyperbolic world, where you actually get a bunch of superrigidity statements of this form. And the point here is, in the complex hyperbolic world, you have two extra tools. You have Hodge theory, and you have algebraic geometry. And those things tend to give you better representation of rigidity. Yeah? Which statement?
How do you get pi 1 in there? So the one I know is the finite volume higher. Pi 1
Yes.
Where's pi 1?
So gamma is pi 1.
Oh, okay.
Yeah. Yeah, yeah. So lattices are always pi 1 of some finite volume manifold. That's right. Yeah.
These are like regardless of age.
What?
These are all like super rigidity.
Yeah. So this is unconditional superrigidity.
Okay.
Here, there's no H in the picture.
Do we know any restrictions of gamma or H in hyperbolic setting that will do super rigidity?
So in the real hyperbolic setting.
Sure.
So I mean, so yes. But none that give you superrigidity independent of H.
Okay.
So there are various incarnations, like, I have a paper with various people where gamma has some conditions and H is not too big, and rho has some conditions, we can prove some superrigidity. There's work on Bruno Klingler on something called fake projected planes, which proves superrigidity of some complex hyperbolic surfaces. That's, well, when H is like GL3, but there's nothing where you can put it, there's nothing I know where you put a condition on, where you have no condition on it. And in fact, I would be skeptical of such a statement. Yeah, I think that you need sort of, I don't know, yeah, okay, maybe I shouldn't say I would be skeptical. But I don't know, yeah. So nothing, but here this is independent of H. Yeah, this one you can change H as much as you want. This is independent of rho as well. And again, it's true for all of them. But here, you have to be very careful.